this is Almost Engineering and I'm Marcus. I wanted to talk about an article I read some time ago. It talked about an endless source of green energy. Naturally, there is no such thing as an actual endless source of energy. At least not as long as the laws of physics don't change drastically. As a side note, the law in question which would require a change is the first law of thermodynamics. It is a law that describes the conservation of energy. It states that the total energy in any isolated system is constant, and that energy can neither be created nor destroyed. If you view the universe as a system, it would be isolated and therefore energy cannot be created, which in turn means that there is a finite amount of energy in our universe. Nonetheless, I decided to look into that claim of endless energy more closely, to see if it was at least referring to a decent source of energy, maybe even an energy source that would be practically infinite for the purposes that we as a collective have. I would consider an energy source to be practically infinite if we could draw energy out of it without having to worry about depleting the fuel source for a really long time. I'm talking about millions of years. So solar power or wind energy is for our purposes practically infinite, since both are enabled through energy radiated from the sun. The sun burns through a lot of fuel, but not in a rate that we have to worry about. Well, actually, some scientists are worried about that and did the calculations, and it turns out that the sun will run out of hydrogen in about 5 billion years. However, in about 1 billion years, the sun will heat up drastically, so that the Earth might get too hot to habitate life. As a side note, this stage in the life cycle of the sun is called the red giant stage. But until then, the sun generates about 384 septillion watts, which equals to about 3.5 times 10 to the 27th power kilowatt hours per year. Now that is what I call practically infinite energy. It is important to note that that energy is radiated in all directions, which means that the Earth only receives about 1.5 times 10 to the 18th power kilowatt hours per year, which is still ridiculous. To illustrate this point further, mankind is currently using an estimated 580 million terajoules per year. This is a number that looks like this. Now, a joule is a rather uncommon unit when it comes to talking about energy consumption in your daily small talk. So that equals to about 1.6 times 10 to the 14th power kilowatt hours. That is still 4 orders of magnitude smaller than the energy that reaches Earth from the sun. And with 4 orders of magnitude, I want to say that at least 1,000 times more energy hits the Earth in a year compared to the globally used electric energy in the same time frame. But enough with the setup. Let's see what the technology was that is a supposed unlimited source of energy. Well, it turns out the technology in question was a subsea turbine developed by the Japanese IHI Corporation. This gave me some hope, since run-of-the-river hydroelectricity and pump storage power plants are amongst my favorite renewable energy sources. Run-of-the-river power plants are in some sense also driven by the sun, since they rely on the evaporation of water, which is enabled by the sun, and the raining down of this water in higher regions. Pump storage power plants also utilize this fact for additional energy generation. However, as the name implies, they primarily use electric energy and convert them in potential energy for storage. As yet another side note, this is the most efficient way to store power, in my opinion, that is currently available. Since ocean currents are mostly driven by wind, they are in extension also driven by solar energy. This is good when you want to claim an endless source of energy. The fact that the IHI Corporation is an established heavy equipment manufacturer since the 1850s also supported my optimism. Even better, they claim to have successfully tested this supposed endless energy source over a 3.5-year demonstration period. Now the sales pitch is to harness the steady and reliable energy of the ocean currents using a subsea turbine, which again sounds like a pretty good idea on the surface. So let's have a look at what they made and how it performed. As you can see here, what they have built is basically a 2-propeller underwater plane. And same as the propellers found in planes, in this case turbines are counter-rotating in the underwater current for stability reasons. Otherwise the machine might tip like a plane would. The central part is a buoyancy adjustment system, which will be relevant shortly. This whole construction clocks in at about 330 tons and is anchored to the seafloor. With the help of the buoyancy adjustment system, it should stay at a depth of around 30 to 50 meters in order to catch the parts of the stream which flow the fastest. This is a critical point, since the flow speed exponentially increases the energy which can be generated. To illustrate, this is the formula for kinetic energy, and as you can see, the velocity in this formula is squared, which means that this is the part of the equation that we want to increase as much as possible in order to have a lot of energy. This would mean that increasing the speed from 1 meter per second to 2 meters per second would increase the energy by a factor of 4. With 3 meters per second, that would result in a 9 times higher energy that could be harnessed. This is a very important fact about kinetic energy in general. Small changes in speed influences the energy levels greatly. The plan is to use the Kuroshio current, which is found near the eastern coast of Japan. This is a very fast current at about 2.5 meters per second, which is roughly equivalent to the Gulf Stream, one of the faster currents that are within the ocean. The main advantage of subsea turbines is that the flow of ocean currents experience very little fluctuations in speed and direction. This should enable a capacity factor of 50 to 70% compared to onshore wind, which is currently around 30%, and solar with about 15% capacity factor. By the way, the capacity factor describes the ratio of the electrical energy produced by a generating unit for the period of time considered to the electrical energy that could have been produced at continuous full power operation during the same period. But how much energy can be harnessed by this method? Currently, they have tested a machine with 100 kilowatt energy output, so 50 kilowatts per turbine. But there are plans to up the turbines to 1 megawatt units, which would result in 2 megawatts per underwater plane. Well, that's just a number, and compared to the annual worldwide energy consumption, it sounds like a tiny number. A fair comparison would be a wind turbine, which currently have power outputs of around 15 megawatts for the largest offshore ones. Here you need to consider that wind speeds fluctuate a lot more than underwater current speeds, which results in a capacity factor of around 42% according to the US government, while the water turbines claim to be significantly higher at up to 70%. If you consider these capacity factors, it would result in about 1.7 megawatts for the best case water current turbine, while the wind turbine would generate about 6.3 megawatts of average power output. Well, after all, that's not a very favorable comparison for the subsea turbines as well. Even worse, the total estimated energy in the ocean currents globally is about 5,000 gigawatts, which is in my opinion quite far off an unlimited energy source. However, 5,000 gigawatts is not that impressive considered that wind already generates 743 gigawatts of energy today. So from an energy perspective, it currently looks like that wind turbines would be preferable if you can build them in a suitable area. But there are a lot of unsuitable areas as well. Maybe they can be utilized by other forms of power plants. When sticking to the subset of hydropower, which focuses on marine technology, the currently most promising competitor to subsea turbines would be tidal energy. So let's look into that real quick to see where the future of ocean energy is more likely to be found. Tidal energy comes in two main flavors: power generation from water level differences due to the tide and tidal flow power generation. Both of them, however, suffer from the same drawbacks. Tides are predictable and move huge amounts of mass, but the process is not continuous. This means that other than underwater currents, the energy production may be limited to a few hours per day. Tidal flow power is conveniently very similar to subsea current power generation, to the point where one might question if they are even different enough to count as separate technologies. To illustrate their similarity, here is a previously discussed turbine setup, and this is the tidal flow setup. They look practically identical, but there is one very significant distinction. Due to the fact that tidal flow power plants are located in channels, they have higher flow velocities to work with. Common are speeds up to 4 meters per second. When we remember the kinetic energy equations, this means that we have 4 times the energy in the stream with equal dimensions, which is nice. The tidal level difference power plants are often formed in artificial lagoons or tidal barrages. They use the potential energy of the tidal movement rather than the kinetic energy in order to turn a turbine and generate energy. Since the moon causes water to rise and lower in an average range of 2 to 3 meters every day, this form of energy seems kind of obvious. The widest tidal range occurs in the Bay of Fundy in Canada, where the sea level changes by 12 meters during the day. The largest level difference power plant I have come across is located in Korea and generates 254 megawatts of peak power. This is an order of magnitude higher than the largest wind turbines and 2 orders of magnitude larger than the subsea current turbines. However, this has to be taken with a giant pile of salt, since the power station is very expensive and has considerable impact on the environment. Not to forget that peak power does not tell you much about the average power output, which might be very limited in tidal power plants. I also stumbled across wave-activated power plants quite frequently.
In fact, colleagues mention them at work and friends talk about them while having a drink, so I imagine you will have a similar experience. Therefore, I will just shortly describe my grievances with them. Wave-activated power is a bit strange, since there are a lot of different ideas how to generate energy from waves. It is hard to explain something without overcomplicating it. So I'll rather oversimplify it instead. Most of the systems I have looked at have some sort of mechanism to convert the oscillation of the water into a way to spin a turbine. By the way, oscillation refers to the up and down movement of the waves. These turbines are usually driven by forcing a fluid past them. Now the problem is that a wave does not have an easy way to make this process in a continuous stream. And interruptions in the flow are very bad for every engineer's best friend: efficiency. Some more adventurous ideas move magnets through a copper coil, which is also rather inefficient due to its discontinuous nature. So in short, since waves move primarily up and down and not forward and backward, it is very hard to efficiently generate power from them. That's why we do not use wave energy, because it makes efficiency sad. A different concept I quite like is that of thermal energy conversion. It uses the temperature difference, or gradient if you want to be fancy, between the cooler depths and the warmer water in the shallows to run low-pressure turbines. This concept is similar to traditional power plants like coal and nuclear power plants, so I might discuss that in more details in another video. But again, in oversimplified terms, these power plants drive turbines by using warm water vapor or a fluid with a very low boiling temperature, like ammonia, because that has a boiling temperature of around -30 degrees Celsius. Due to the small temperature difference, it is not the most efficient way to generate energy, since the efficiency of turbines increases with the temperature difference. And water from the depths is at max 25 degrees Celsius cooler than the surface area water. Nonetheless, they run continuously and very reliably. They are quite easy to maintain and are not too complicated, which make them more affordable. The only reason why this technology is not widely adopted yet is the low degree of efficiency due to the small temperature difference. Another possible way to generate energy from the ocean is osmosis. Osmosis is a bit like witchcraft to me, so I will try to explain it as best as I can. It requires 2 containers with water of different salt levels. The containers are connected by a membrane, which only lets water molecules through. Since the salty water pulls water molecules through the membrane due to witchcraft or something, the pressure in the salty container rises. Now, when you put a turbine over the container, air and water vapor will try to escape the container due to the higher pressure and turn the turbine. The higher the difference in salt levels, the higher the pressure over the salty water. And in turn, the higher the amount of energy you can generate. Osmosis has the drawback that it turns fresh water into brackish water, which is water that is saltier than fresh water but not as salty as seawater, and that the cost of the membrane has been an obstacle. In conclusion, there is almost limitless energy available to us, which is provided by the sun, And we should take advantage of that fact. Subsea turbines are, in my opinion, only suited for areas which do not allow for wind turbines, but they still have advantages compared to other marine-based power generation. Tidal power plants suffer from low capacity factors and bad environmental impacts, while wave power plants and thermal conversion power plants do not provide huge degrees of efficiency, and osmosis power plants use fresh water and suffer from the problem of finding good membrane materials. But at the end, just a small disclaimer. This was a quite narrow look on the topic of power generation in an oceanic environment, and left out some very important discussion points. Primarily, the environmental impact of all marine power plants is quite severe, while wind turbines have very little effect on the environment. From an engineering perspective, a quite important topic is also the effect the environment has on the power plant. In short, corrosion and abrasive phenomena are quite severe in an oceanic environment, and therefore this would be another point in favor of wind energy. And with that, thank you for watching, and please leave a like or subscribe to my channel.